Hello, welcome to ISAT 330 Sustainable Manufacturing Systems. This is lecture 1. So in this lecture, I will give you an overview of this course and also talk a little bit about manufacturing fundamentals. My name is Hao Zhang. I'm assistant professor at the School of Integrated Science at James Madison University. Well, the lecture will be composed of 3 components. The first, I will give a little bit introduction about myself, and then I will give you an overview of this course and what need to be considered and take care of when you are taking this course. And lastly, I want to give a review of what was covered in 2011 about cycle time analysis and other manufacturing fundamentals, so you are better prepared for this course. My name is Hao Zhang. The first name is H-A-O, Hao, and my last name is Zhang, Z-H-A-N-G. In order to help you pronounce my name, you can pronounce this Hao as Hao and Zhang as Zhang. And this is the closest pronunciation to my Chinese name. You can call me Dr. Zhang or call me Hao. Either name will be fine. I grew up in central China. It's a small city, but it still has 8 million people because of the high population in China. And I grew up there, had my elementary school through my high school. The Shangqiu city is actually an Asian city. And these are the pictures of the Asian city. You can see there's a gate. So the gate is actually one of the gates. There are 4 gates around the city, and this is the inside of the city. And this picture is a sky view of the city, and you can see it's more like a square, and it's surrounded by a protection river, so that's more for defense purposes. But right now the city is more like a modern city because the Asian city is it's not within the current city, and that's more of a preserved area for tourism. So the red bottom corner is what it looks like right now. And then after high school, I went to a college in Beijing, and I got my bachelor degree in 2009. And then I moved to Corvallis, Oregon, and pursued my master's degree and also PhD degree. And then right after I graduated, I moved to Canada. So I was working as a postdoc associate in University of Alberta in Canada. And then in 2016, I got an offer from James Madison University and joined here as assistant professor. A little bit background about myself, industrial background about myself. So my experience in industries really started from my childhood when my mom actually was working as a worker in a publishing factory. While at that time it was 1990s. The regulations are not well established. So as a kid, I was able to play in the factory or factory area, and I got to see many different processes and how the factory works. But right now it's not gonna happen because it's it's kind of for kids it's not an area to play with. And now, actually, I'm still working with some of my friends who have established their own factories in my hometown, and I'm helping them to establish their own processes and also their management and also quality control. So more of a consulting work with them. So in China, when I was in Beijing, I had some of the interns, and I was working as an intern in a Beiji Fulton Motor Corporation. So the factory was making, buses or tractors. Then I was there to conduct some of the projects and also work as an intern to collect some of the data for the management. And then in graduate school, I got a chance to work with multiple industrial collaborators in different industries. So one is the Benchmade, so they are making knives. So those knives are used really for outdoor activities or military purposes. And also, I work on a project with Sheldon Manufacturing, where I spent almost 2 years with their employees as well as the management to fully study the company from the mechanical or manufacturing process to the management part. And in Canada, I was working as a research associate, so I had a bunch of projects related to industrial collaborators. For example, Sancor Energy, I was working on a project related to GHG emissions related to reclamation. And also developed the process for for producing biofuels from municipal solid waste for Anacam company. Currently, in Virginia, I'm also working with some local manufacturers trying to initiate some research projects for students. In terms of my academic background, I got all my degrees in industrial engineering, and and you can see my research areas. Well, with all my degrees in industrial engineering, but I have different focuses at different levels. For a bachelor degree, it's very general, i.e., knowledge. But in my master's, I was focusing more of a mechanical engineering. For example, I was studying more of tool life, machining, and the processes. Well, in my PhD study, I focused on more theory and system engineering and system thinking, how that is related to manufacturing process and system improvement. And so for these research areas, if you're interested, you can do a little bit of research and understand what these are about. And if I'm interested, you can also contact me and we can discuss those research. All right, next let's talk a little bit about what this course is talking about, and also where this ISAT research resides in manufacturing curriculum in ISAT. Now let's start with 211. So 211 is your second year, which you have taken, and that is manufacturing fundamentals. Of course, that was a different name. But the topics have been covered are principles of making, designing, or advanced manufacturing, continuous improvement, production systems. You get a chance to see a little bit here and there about manufacturing systems. Then in the third year and in the fourth year, we will get a chance to get into more in depth about each of the aspects of knowledge in manufacturing. And so in the third year, there will be 3 courses at the sector level. The first one is 330, so which mainly deals with production planning and control, and it includes the inventory control, computer integrated manufacturing, facility layout, capacity planning, forecasting, scheduling, supply chain, quality control, engineering, economics. So these are the management part of the manufacturing called knowledge. And also there are a lot of technical part about manufacturing knowledge, which includes manufacturing automation. So that's covered in 331. Human factors economics, as well as cyber physical systems. So these are dealing with some of the hard components like sensors, actuators, motors, some automated controls, and per PLC, material storage, and also device and equipment, robotics, those kind of manufacturing knowledge. Another important aspect is human factor economics, so which is to take care of the well-being of the workers and employees. And for cyber physical systems, these are more for smart systems of the manufacturing systems. And we have another hands-on course, lab course, which is 1 credit. That is mainly about manufacturing automation. So that's here, 303. So in 303, you will get a chance to use sensors, actuators, and some other devices to establish a programmable logic control system in order to achieve certain automatic function of the manufacturing systems. So this is a third level, 300 level courses. And if you want to concentrate in production systems or manufacturing, there are also a lot of knowledge you can learn, and these a lot of them are offered in our fourth year level. The first one is 430. So that's materials and manufacturing processes. So if you want to know manufacturing, you have to understand the materials and how the materials are used in design, in production. As well as manufacturing processes. There are tons of manufacturing processes. In 430, you're going to cover mostly the traditional processes that have been existing for maybe hundreds of years or decades. And another component of 430 is computer-aided design and manufacturing. So here you will be able to design an actual product with consideration of production, designing, as well as many other aspects. For example, engineering drawing and GD&T, and so that's the 430. It has both a lab and also lecture sessions. And another course that will be 431. So this course it deals with more advanced manufacturing processes or novel processes such as 3D printing, additive manufacturing, or micro manufacturing, nano manufacturing, and digital manufacturing. And so compared to the first 30, these processes are more novel. So you have to understand a lot of other technologies, for example, laser technologies, as well as materials, and how that be used in future manufacturing systems and processes. We have the technical part. We also have management part of the manufacturing knowledge in a concentration level. For example, 433 and 435 are talking about Lean Six Sigma and continuous improvement. So if you're interested in management or operations management of manufacturing systems, here these are the courses you might want to take in order to achieve maybe yellow belt or green belt or even black belt of the Six Sigma. That having that certificate will help you find a job in the market. Well, another course is a 437. It's about technological innovation and sustainable designs. Mainly, it was looking at how to make sustainable designs with different technologies, and also what are the policies, regulation related to design and technological innovation. Another course is about manufacturing informatics. So here we use data science or data analysis in order to improve the quality of the manufacturing process and systems. You will learn different measurement systems, the process improvement, as well as design experiment, reliability modeling, data acquisition, and big data. So that's all related to manufacturing system. So from this description, this map, as you can see, so 330 is actually only one corner of manufacturing knowledge. So do not think that after you've taken this course, you know everything about manufacturing. It's not the case. But 330 will give you a kind of good knowledge related to manufacturing operations. You got to know more about manufacturing systems. All right, now let's look at the syllabus, and this is my email address. You can send me an email if you have questions, or you want to schedule a meeting. I'm always happy to discuss with you. And for the course objective, the idea of this course is to have you understand the components of manufacturing systems, the planning and control of production, and as well as quality control in production. And lastly, there will be some lectures related to lean and sustainability of manufacturing systems. Textbook. There is a textbook for this course, but it's not required. And because there are some examples, some of the items are actually from this textbook. So if you are interested, you can buy this, but it's not required. 4 major topics will be covered in this course. The first one is the manufacturing fundamentals review. Second one is production planning and control. Here in production planning and control, we're going to discuss scheduling, capacity planning, inventory control, facility layout, supply chain, those kind of things. And in quality control and inspection, we're going to talk about different models of quality control, the measurement, and also some different inspection devices. Lastly, we'll use some lectures to discuss how can we make or improve the efficiency as well as cost, economic, and environmental aspect of manufacturing systems. So if you need any accommodations, make sure you work with Office of Disability Services, and then send me a formal email. So about what happened and also what accommodation you need. I'm happy to help you. Please make sure you always follow the honors code. I don't want to see any cheating or violations of the honors code happen in this class. But if it does happen, then I'll have to work with you to find a solution. All right, now let's move to manufacturing fundamentals. So here we're going to give you a recap of what is covered in 211. Then we're probably going to get a little bit more in depth about those. First, let's look at how the products are made. And the products are made actually from the concept design. First, we need to know what do we want to make, right? And from the concept design, then we'll move to the design research and development, because you have to realize the concept to actual technology and the functions. So that's the R&D will happen. And then from that, you come to the product design solution, right? So get into production part, for example, what dimensions, what kind of properties, what kind of specifications need to be realized from your design. Well, the last or the output from this design is actually the prototype to make sure a can achieve the functions that is from the concept design, as well as the product you make also fulfills the customer's need. Well, in terms of how to make the prototype, there are two different ways. The one is if you have already have a manufacturing system on your shop floor, then you can just realize it from your own production systems. And if you do not have a shop floor to make them, sometimes you can always outsource this from a workshop or other factories to make the product for you. Well, then after you have the design, then you will have to make them in a manufacturing system or the production system. The most important part of the manufacturing system is the manufacturing processes and also the other operations. And for example, if you are making say 1,000 cell phones a week, then you want to figure out what are the manufacturing processes that are involved in making cell phones, and what are the assembly operations there. But that's not all, because there are a lot of other supporting functions related to manufacturing systems. For example, inventory control, scheduling, right, the layout, continuous improvement, and quality control. That all comes into play in order to facilitate the manufacturing processes. Well, when we look at the production system as a whole system, then there are the input and also the output. The input will be the engineering materials, and the output will be the finished products. Now let's look at after we made the product from the manufacturer, what's going to happen along this life cycle. So first, it will go to a distributor. So the distributor will sell it to the users. And the users, after the use phase, there are multiple ways to deal with it. The first maybe you can just dump it to the landfill, and then after maybe 100 years, it will be decomposed and into natural materials and extracted by some companies, and then being processed into a certain material or in a certain shape that is ready for manufacturing to make other products. Well, there's also another way, which is to recycle it. For example, after I use a cell phone, there are some metals, there are some other rare metals actually can be recycled and go to the material processing facility immediately instead of sitting there for hundreds of years. It also happens a lot in our society. And another way is the remanufacturing. So which means a term you probably hear a lot is the refurbished, right? So it means there are some of the defects or after use phase there are some kind of problems or going through this dead end, but there are a lot of actually components of the products are in a very good shape. So in this case, you can always send it back to the manufacturer, and then they can make it into a brand new product out of it. And so that's remanufacturing, and of course, you can recycle or reuse it by some other users and send it back to a distributor, and this distributor will sell it to some other users. That's selling it as a second hand. All right, so this is what happened with the product life cycle. Remember this product life cycle is very important to have a entire overview of what's happening with all the materials and the products along the life cycle. Now let's look at what's within the production system or the manufacturing system. I look at it as three different layers: the demand, production planning, and the shop floor control. At the demand layer, really think about if you are a boss or CEO of the company, what do you want to do? You first need to understand what is the demand, right? By the customers. Do we have a big market, or do we not have a big market? Is there a seasonality, high and lows of the sales during the year? So that's the first step you need to understand about the market, right? So that's a demand level. And in our course, I'm going to talk about forecasting. So you have a good idea of how do you forecast the demand over the year. And the next level or layer is production planning. In production planning, so after we know what is the demand throughout the year, then we will put into practice of making them. And how to make them, then we'll make a really good schedule. The schedule which involves of how do we plan out the materials, how do we plan out the processes, and how do we plan out all the other resources in order to achieve all the functions of making those products. And those will be different lectures in this course. For example, MRP deals with planning out the materials. We do not want to have all the materials available at the same time, even though they are not used at the same time, right? Because the storage of the materials is also a cost. So that's why we want the material arrive at the time they should arrive, or at the time we want to use it. And then the next layer will be the shop floor control. So this will be more of improving the efficiency of the production. So, for example, the quality and the sustainability, we want to make sure our system is efficient and also economic, right? Environmental friendly and also social friendly. So, as well as how can we make a good schedule that can reduce the lead time and the cycle time of our production. All right. Usually I start with a simulation game. So the game is about making paper paper airplanes. So I designed the 4 steps to make a paper airplane. Of course, there are many different ways to make them, but I just use the standardized operations or standardized steps to make them. And this simulation is about testing or understand 4 different production setups and what are the differences, and also get to understand a little bit about cycle times. So the 4 setup will be the A, B, C, and D. A is about each operator. Oh, by the way, there are 4 operators in each of the simulation game. And in A, each operator will be making their own paper airplanes. So which means that they grab a new paper and then finish all the 4 steps all by himself. Well, the B is a bit different. They form a production line. Each operator is only responsible for 1 step of making the paper airplanes. And C is that they will form 2 work cells. So 2 work cells means in work cell 1, here in work cell 1, they will be responsible for the first two steps, and it doesn't really matter who finished first. As long as they finish the first 2 steps, they will put it here to give it to the next work cell. And then whoever is available in the next work cell will grab it and then finish the rest 2 steps. So this is called work cell setup. And the last setup is a batch production. It's a batch production setup. It's similar to B, but the difference is that B only produces 1 part at a time and then send it to the next step. While for D, it will first finish 5 parts at a time and then transfer it or give it to the next step. So which means each of the operator cannot give it to the next step if they haven't finished all the 5 parts at a time, right? So from past history data in the past years, what I noticed that usually the highest outputs through the 5 minutes operation always come from A or B. And then slowest will be the D. The reason behind this is because in D there are a lot of waitings because for the second operator here, he probably won't be able to get to start until all the 5 paper airplanes will be all the 5 steps, all the 5 parts will be made. So that's why it causes this kind of result. Then let's look at the cycle time analysis. So first understand what is cycle time. So cycle time is really the time between 2 successive deliveries, or you can say it's how often a part or a product is made, right? So we say, hey, 1 product was made at time 0, then after 2 seconds another part was made, after 2 seconds another part is made, and after 2 seconds another part is made. So the cycle time will be 2 seconds, right? And the takt time is a little bit different. Takt time means that it's a maximum acceptable time to meet the demands of the customer. So this is more from the customer's perspective. Think you are the customer and you tell the factory that by the end of this year I will need 100 airplanes. Right? It doesn't matter paper airplanes or airplanes. You just say airplanes. Well, for the company, it has a 1 year time, right? Say you place this order or you make this request at the beginning of the year and you want it to be delivered by the end of the year. So the the factory will have a whole year time to make all these 100 airplanes. So that's a takt time, right? So takt time equals to night time available for production divided by customers. Let's not say daily demand, but customers' demand. Okay. All right. So the next lead time. So the lead time means the time from request to delivery. It's simple to understand because you probably have been doing this a lot. Think of it if you are ordering a pizza from Pizza Hut or Domino Pizza, right? From the time you make the call to the time your pizza arrived at your home address, right? So that's the lead time, right? That's the lead time. And same with the factory, from the time you place an order at the factory to the time that is, all the products have to arrive at your address. So that's the lead time. Then next is the work content time. So work content time means a sum of cycle times all process to make a product or component. So what does it mean? It means making this, for example, making one product requires several processes, right? And each process requires a certain processing time, right? So the work content time is the sum, so all the process times from all these steps added up all together. How much time is required to make one product, right? You might want to differentiate this with cycle time. So cycle time means how often we can make one product, while work content time is what is the sum of the times to process one finished product when it goes through all the steps. Next, I'm going to use an example to just further explain this. All right, so the example is that a customer just placed an order of 75 airplanes and need to get them 2 hours later. Right, it's probably paper airplanes. Assume it takes about 10 minutes to process the order before putting the order in the production line. It takes another 10 minutes to deliver to the customer's address, while the 75 airplanes were actually delivered 60 minutes after the order request. And also, you can see the process times here. Step 1 takes about 6 seconds, step 2, 8 seconds, step 3, 5 seconds, and step 4, 7 seconds. Well, here you can see from a timeline, we placed the order, or order was placed at the time 0, and we requested the delivery time is 120 minutes, so which is 2 hours later. But actually, the order was delivered 60 minutes later, right? So this is what happens. And now let's look at what is the takt time in this case. So takt time, remember, that is the net time available for production divided by customer's demand. Here in this case, what is the time available for production? Well, we asked the products to be delivered by after 2 hours, right? So the 2 hours window or 2 hours time is the net time available for production for the factory. So 120 minutes divided by customer demands. How many airplanes are demanded? So 75 airplanes. So it equals to 1.6 minutes per airplane. So this is a takt time. While the lead time means from the time you place the order to the time when the order was delivered, right? So the order was delivered actually 60 minutes later, so which means that it's 60 minutes for the lead time in this case. All right, next let's look at cycle time, work content time, and service time, and repositioning time. What this means. We know that for the first steps, each step takes their own processing times. For example, step 1 takes about 6 minutes, step 2, 8 seconds, step 3, 5 seconds, and step 4, 7 seconds. Well, let's first look at work content time. So work content time means what are the actual processing times that are required to finish all the steps to make this one product, right? So you can see, let's look at first step 1. Step 1 here we have 6 seconds of operation time, but not all the 6 seconds are actually working on the part. That's because 5 seconds are actual processing the part, but 1 second is doing what? Is just doing the repositioning. What does it mean by repositioning? Repositioning means it's a time from finish of the prior operation to being ready for the next operation. suppose you are operator are operating a machine, automated machine, right? First step you want to do is actually put the parts on the machine, right? And then run the program, let the machine run the program, and then you unload the part from the machine, right? So during these operations, there are times. So loading the machine, unloading the machine, these are the repositioning times because you are getting ready for the next step, right? Sometimes it also is the transportation time, right? You want to pass it to the next operator, so that's also some time. So here in step 1, you can see the 6 times of the operation. That's the cycle time for step 1. Well, also it composes of a processing time, which is 5 seconds, and also 1 second of repositioning time. So that's why the work content time for this product, for this airplanes, is actually composed of 5, 7, 4.5, and 6. Those are the times that actually processing on the part itself. Alright, so that's work content time. Now let's look at what is the cycle time. Remember, the cycle time means how often you can get a completed part or product. Well, of course, it really depends on what you're talking about the cycle time. Are you talking about one single process, or are you talking about the whole system? If it's a single process, then the outcome will be a part. If it is it's a process, the outcome is a part. If it is a whole system, then the outcome will be a finished product, right? So now let's look at step 1. The cycle time is actually 6 seconds because every 6 seconds you get a finished part, right? Every 6 seconds you get a finished part. While for operation 2 is the cycle time for operation 2 will be 8 seconds because every 8 seconds you get a finished part. Now the interesting part, it will be step 3. So what is cycle time for step 3? Well, cycle time for step 3 is actually when we are only looking at the step 3 alone, then it's 5 seconds. But when you are looking at the whole system, what happens is that step 3 will have to wait 3 seconds before it can process another part. Why? Because step 2 actually takes 8 seconds, right? Step 2 takes about 8 seconds, and it won't finish its production. It won't finish its part until 8 seconds later. And 3 already only used 5 seconds to finish the one part and have to wait for another 3 seconds to finish. So that's why, from whole system perspective, 3 will have to wait, right? That's and step 2 is the bottleneck. Same thing with step 4. Step 4 takes about 7 seconds to finish its own operation, but it has to wait 1 second until step 4 can start to make another one. So that's why from this whole system, the cycle time is actually the longest, right? The longest processing time. Plus it's what? It's repositioning time, right? This is the processing time and the repositioning time. So this is the largest one. So that's why for this whole system, the cycle time actually equals to 7 plus 1, 8 seconds. Because 2 is the bottleneck. So that's why just remember in the production systems, the longest processing time is actually the sunken cycle time. That determines the cycle time. All right, now we have a better understanding about cycle times and also work content time and also repositioning time. Next, let's look at line balancing. Okay, so line balancing means you can see all these 4 processes that they do not have the same processing time, which means some will be bottleneck, some will be waiting, some will be finished early. Okay. Well, in this case, we use a line balancing efficiency to describe how efficient or how balanced these processes are. Because the ideal case is all the processes have the same, right? Have the same processing time. Now let me ask a question. we have this system. Is there a way that we can reduce the whole cycle time to 6 seconds? So is there a way to reduce this time, this system's cycle time to 6 seconds? Yes, there is a way, right? Because look at if we disassemble 2 into 2 operations, so what's going to happen? It's probably going to be what? Going to be made of 4 plus 4, right? 4 plus 4. And then we decompose step 4 into 4 and 3. So remember, among all the processes, which one determines the cycle time of the system? It's the longest processing times, right? In this case, after we decompose some of the operations, actually we get the highest processing time will be 6 seconds. So in this case, we can make this whole system, the cycle time to be 6 seconds, right? Before it was 8 seconds. So this is the way that you can increase the production pace or or reduce the cycle time of the production. All right, now let's come back to line balancing efficiency. If the line balancing efficiency is really high, means what? Means it's really balanced. But its line balancing efficiency is really low, means there are some of the processes that are really creating bottleneck. You need to make some pre-improvement on that. Well, the equation to calculate the line balancing efficiency equals to the top part will be all the processing times added up together, divided by, assume that all the processes have the same longest processing time, right? Just assume all the processes have the same longest processing times. So that's 4 times 8, right? In this case, we got 81.25%. All right, next let's look at the how do we determine the number of workstations if we know the work content time and the longest service time. So think of a product was required a total working content time or certain time to make this product. Then how do we determine number of workstations? Well, if we know for each of the process how much time it takes, right? Then we can use the total working content time divided by what? Divided by the longest service time. Then we can get to know, okay, how many of those blocks are, how many of these workstations are. But remember, there's also a line balancing efficiency because it's not always all these processes times are the same. So we need to multiply the line balancing efficiency with this longest service time, right? So we use this equation to calculate the number of workstations you need. All right, now let's look at another example to describe production rate. Okay, so production rate means number of goods can be produced during a given period of time. What does it mean? It means, all right, for example, during the 8 hours working hours of the factory, right, it's from 9 to 5 p.m. But it's not always that the machines are running. It's not all because there are some breaks, restrooms, or lunch times. So these are the time that is no actual production, right? So there's no actual production, which means the machines are not running, the production line is not running, they are not making anything. And only the green times, you can see the green segments are actually making parts. In this case, even though we have 8 hours of working time, but the actual production time is smaller or shorter than the 10 hours, than 8 hours, right? So here we can use the line efficiency to describe this. So line efficiency equals to the production time divided by total working time, right? Also, we can calculate it by using cycle time divided by production time per unit. So production time per unit means what? Means during the 10 hours time, during the 8 hours time, how many parts, how many units are made. Right? How many hours, how many units are made. I don't really care how much breakdowns you have, how much it's lunchtime. I only need to know you have 8 hours working 8 hours working hours, and those are the total number of products you made. So this is the production time per unit. But a cycle time is different. So cycle time equals to what? Equals to, remember, longest service time plus repositioning time. So it's assuming that there's no breaks, everything's smooth, every time is moving, right? So this is cycle time. So that's why cycle time equals to the production time per unit times the efficiency. Now let's look at this example. In order to calculate line efficiency equals to what? 8 hours minus 75 minutes. 75 minutes, that's 5 times of breaks. Each break is 15 minutes. So 5 breaks, so there will be 75 minutes. And the lunchtime is 1 hour. So use 8 hours minus, which is 480 minutes, minus 75 minutes, minus 60 minutes, divided by 8 hours. So that's 480 minutes. We got the line efficiency is 71.9. So here you might want to differentiate the line efficiency with line balancing efficiency. Remember, line balancing efficiency means how balanced those processes are, right? If it is the same, if there are too much difference, that's line balancing efficiency. Well, line efficiency means there are some of the times that actually is no production, right? So that's the line efficiency. And well, the production rate actually equals to the number of units produced divided by the total working time, right? That's the production rate. And equals to 1 over cycle time. So what does it mean by 1 over cycle time? So 1 over cycle time means how many units are made per time unit, right? Remember, cycle time is how much time per unit. Well, the 1 divided by cycle time will be the unit per time, right? But this part is based on the assumption that there's always smooth production. There's no breaks, right? There's no downtime. It's always making production is always running. But it's not always the case because there's the line efficiency, right? It's the line efficiency. There are breaks. So you use this part to times the line efficiency to get the production rate, right, of the company. As an example here, let's now assume that the cycle time is 1.5 minutes per product, right? What is the production rate here? If you want to know the production rate, now let's first look at, okay, what is the number of units produced during the 8 hours? So during 8 hours, actual production time is what? Actual production time is only 345 minutes of production time, right? So we use 345 minutes divided by the cycle time, 1.5, then we can get 230 units can be made in the 8 hours, right, for the 480 minutes. So in this case, we can find out how many products or units are made. Then we use that to divide it by the total available time, so which is 480 minutes, the 8 hours, working time. Then we get 4.48 unit per minute. So this is the production rate. Well, this is one way to calculate production rate. Another way, which is use this equation, right? 1 divided by cycle time times line efficiency. We already calculated line efficiency is 71.9%, and we know the cycle time is 1.5, so we can calculate that is the same. It's 0.48 unit per minute. All right, now let's look at one example here. So a manual assembly line is being planned for a product whose annual demand is 90,000 units. A continuously moving conveyor will be used with work units attached. Work time is 55 minutes. So the line will run 50 weeks per year, 5 shifts per week, and 8 hours per shift. And each work will be assigned to a separate workstation based on previous experiences. Assume line efficiency is 0.95. Now we have this line efficiency. Balancing efficiency is 0.93, and repositioning time is 9 seconds. So we got a lot of information here. Now it asks us to determine what is hourly production rate to meet the demand. Okay, hourly production rate to meet the demand. Now it's asking for production rate. Remember, how do we calculate production rate? Production rate means equals to the number of products are made or need to be made, number of products divided by available time. Well, in this case, how many products need to be made? It's 90,000, right? It's 90,000 products need to be made, and available time will be how many hours? Because it is asking for hours production rate, so we need to convert all the units into hours. How many hours? Yeah, we know that 8 hours per shift. Okay, 8 hours per shift. And how many shifts? Okay, 5 shifts per week. 5 shifts per week. And how many weeks? 50 weeks per year. So this is the annual demand, right? This is the annual time, or available time. In this case, we can calculate what is production rate. How many products need to be made per hour. So this is how we get the production rate. The actual time is, the actual production rate is actually 45 units per hour. Okay? All right, next, the second question is asking the number of workers and the workstations required. In order to calculate the number of workers and workstations, let's assume each workstation only requires 1 worker. Okay, so basically, number of workers or workstations equals to, remember, work content time divided by what? Divided by longest service time times line balancing efficiency. Maybe. Okay, line balancing efficiency. Do we know work content time? Yes, we know work content time is 55 minutes. Okay. And do we know line balancing efficiency? Yes, we know line balancing efficiency is 0.93. So in this case, we just only need to find out what is the service time. All right, do we know service time? Right now, we do not know service time. So our task will be to find the service time. So remember this equation which is called CTC, which is cycle time, equals to longest service time plus repositioning time. Okay. All right. So do we know repositioning time? Yes. In the question we know the repositioning time is actually 9 seconds. It's 9 seconds. And we want to find out service time. So we just need to know what is the cycle time. Well, can we find out the cycle time, right? If we can, now the question is, as long as I can find this cycle time, I can find out, this answer. Well, the cycle time equals to what? We already know the production rate, and we already know the line efficiency. We actually can find out the cycle time because what? Production rate equals to 1 divided by cycle time and times line efficiency. Line efficiency, right? We know line efficiency is 0.95. We know the production rate. Now we can calculate the cycle time. So from this, we can find out how many workstations we need in this case. So these are the calculations. So you can go through those calculations and find out the answer. So here it's calculating the cycle time. Now we calculate the longest service time, and then we can find out the total workstations. All right, so all these calculations from the past are for manual operation lines or manual operations. So what about the cycle time analysis in automated lines? So is it different or the same? So first, let's look at what are characteristics about automated lines. As we know that automation, there are some common configurations. So one is the inline configuration, which means that you have workstations along a transfer conveyor, right? The parts will be on a conveyor or on the transfer line, and then when it goes through each of the workstations and being processed one after another. Another setup or another configuration is the rotary, so which means the parts will be on the conveyor transfer table or transfer belt will form a rotary shape. It will go through one station by another through a circle. Another setup will be the carousel setup. So let's see, it's similar to the rotary, but it can hold actually more machines on it. So you can watch this video and see how these setups are actually realized in a production simulation or actual system. Well, as for the cycle time analysis, actually a lot of time it's similar. As long as we understand the fundamentals about all the reasons to calculate those times. For the cycle time in the manual assembly line equals to service time plus repositioning time. Well, for the automated lines, it actually equals to the same thing. Right? We find out what is the longest service time plus its repositioning time. Right? Or sometimes they can be, it's a transfer time. While the production rate, it's the same. Production rate equals to 1 divided by the cycle time plus the downtime, right? Cycle time plus the total downtimes. This is because if it is only cycle time assumes that the production line is always running without interruptions, without any breaks, but there actually are some of the breaks, so we have to count them together. So in this case, when you use cycle time plus the downtimes, I use 1 divided by that. Excuse me. Well, how do we calculate the downtimes? Well, the difference between the manual and the automated line is that for automated lines, once one machine is break down, actually the whole production line won't be working, so will be stopped. So the downtime frequency can be calculated by added up all the probabilities of their breakdowns. Right? For example, we have machine 1, machine 2, machine 3, and then probability will P1, P2, P3, and the downtime frequency and the probability will be equals to P1 plus P2 plus P3. Well, if P1 equals to P2, P3, then we can use this equation to just use number of machines times each of the probability, right? And the line efficiency it's the same, right? Using production time divided by total working time, or use cycle time divided by production time per unit. All right, now let's look at another example related to automated production lines. It says that an automated transfer line has 20 stations and an ideal cycle time is 1 minute. So probability of a station failure is 0.01, and the average downtime when a breakdown occurs is 10 minutes. So determine the average production rate and line efficiency. So in order to find out the actual production rate, we need to do what? We need to first find out what is the breakdowns, right? So breakdown will equals to what? Equals to all the probabilities added all together about this production line. Because here we have 20 stations, and for each station the failure probability is 0.01. So the probability will be 0.01 times 20, which is 0.2. And then after that we can calculate what is the actual, right? What is the actual production production time. So actual production time will be per unit, as here it's called per unit. Equals to the cycle time plus the breakdowns, right? Cycle time plus the breakdowns. So it will be 1 plus 2 equals to 3 minutes. And then next, the production rate will be equals to 1 divided by production time per unit, right? So because we want to convert it from hours to minutes, so we have to use 60 to divide by TP. So here we got 20 pieces per hour. And then line efficiency, we just use cycle time divided by the 1 divided by the production rate, because the production rate does already counted for the efficiencies, while the cycle time only assumes that the production line is always running smoothly. So that's why you can use this equation to calculate the line efficiency. All right, next I'll discuss a little bit about cellular manufacturing or group technology. So cellular manufacturing or group technology means that we can group some of the machines or some of the process together as a cell, instead of spread it out into different processes. So there are a lot of pros and cons, and later I'm going to talk about that. But first, let's look at how can we make those cellular manufacturing happen. Well, the cellular manufacturing actually only fits with certain criteria when that we have similar products or the products go through similar processes, right? But how can we tell if they belong to the same part family? Sometimes we can tell from its outlook, right? It looks similar, then it probably it belongs to the same part family. While sometimes it looks different, but they actually go through the similar processes, then we can also put them into the same part family. I'll say but sometimes, but it's not always. So the reason I'm saying it's not always is because, for example, this is A and B pictures. For A and B, they are looking pretty much the same, right? But the difference is that the material is different. And for A, it's nickel-plated steel, while the B, it's stainless steel, and the tolerance are also different. So the tolerance for the first one is plus minus 0.01, while the tolerance for B is 0.001 inch. Don't just think it is only one little tolerance difference. It actually can cause a lot of troubles when we are trying to reduce the tolerance. To make tolerance more strict, right? So because if you want to make it 0.01, we probably have to use a totally different process to make it, or a totally different machine to make it. So that will increase the cost for resource, and also the time to make it. So that's why it's not always that the look will determine that the parts belong to the same family. All right, so what are the ways to identify part families? As I mentioned before, you can look at it from the look, visual inspection, or you can look at analyze its processes, right? In order to make that part, what processes need to be, gone through, right? And then if they, go through the similar processes, then you probably can group them together as a part family. Another one is you can actually group the part family by the coatings. Actually, the coatings are developed because of the analysis, because of the data, right? Because if part A need to go through, say, surfacing, drilling, and milling, then it has a certain code, right, with numbers or letters. And if another part goes through a similar process, then it will give a similar coding or letters. So from the letters and codings, you can actually see they probably can belong to the same family. So this is different ways to identify part families. Well, the benefit of the part coding A lot of benefits because right now in companies the people are organizing the information and using this information by using computers operations, and the computers can only recognize certain numbers and letters and codes, right? So it can actually make it a lot faster to get the information you need. So it's like your ID, student ID. From your student ID, I get all the other information related to yourself, right? So that's why coding them, they can facilitate the formation of part families, permits quick retrieval of the part design drawings, reduce the design duplication. So because once I know that that kind of code is already existed or that part is already exist, I do not need to draw another or make another design out of it, because that kind of design already exists or similar design already exists. And also promotes design standardization. So design standardization is very important because if it is not standardized, it's gonna give a lot of troubles. Think of the threads and screws, right? You go to the market and you'll find a different model of the screws, and if you know the model, you just find it out, right? But if you have a machine or you have a certain equipment that requires just a slight difference with a standardized screw, and you cannot find it from the market, well, in this case, you got a big problem, right? And also, this is often happens with, it's actually the disconnection between the design and the manufacturing. So a lot of times designers will design something that is only a minor difference, but it causes a lot of problem in producing it. It's because the manufacturing shop floor will have to develop certain tools, certain maybe devices, and also make certain setups in order to make that that difference. But actually, that design will not make a difference in the function itself. So in this case, making all these designs standardized will be very important. And also, using the coding will help you do the cost estimation and cost accounting, because all the information can easily be tracked. How many parts have been made, how many parts have been used already, or in the inventory. So I easily calculate all these countings. And also, we can facilitate NC part programming by allowing new parts to use the same part program as existing parts in the same family. So a lot of times those kind of part programs are actually associated with the part numbers, right? And if you know the new part will go through similar operations, you can probably use existing programs as part of the operation, right? And then you just add another, maybe a certain program on top of it in order to save time or save effort to make those. And the last part is computer-aided process planning becomes more feasible, because once all the codes are developed, in this case, you can actually make this kind of planning easily. Well, next, let's look at a composite part. So composite part is used to describe a part that is composed of several processes together. For example, this part A on the left, you can see it's a round part. It has a rod. It looks like there's a ring at one end. Well, in order to make this part, it has to go through several processes. For example, the first process will be probably the turning process, in order to reduce a certain reduce the diameter to a certain dimension. Well, the next one will be maybe the facing operation, all right, surface operation. Then the third one will be another turning operation in order to make to reduce diameter from here to here. Then the first one will be probably the surface, because it wants to achieve a certain quality of the surface. So it's more like a grinding process. And the fifth will be creating this kind of central hole. So in this case, it will be a drilling process. And five. Sixth will be the counterboard to create this part. and 7 will be the typing to make this threads. Well, you can see just to make this one product or one part, it's actually gonna go through several processes together. As a production planner, you probably don't want to make all these machines so isolated that the operator will have to go to here and there and then come back here and there to make this part, right? Maybe you can just group all these machines together so the operator can just use one machine after another to make the whole part. Then it saves transportation time, and also it saves setup times. These are the operations actually made for each of the part features. You can see the axial cylinder is the turning, the face of the cylinder is by facing, and the cylindrical stab is by turning, and the smooth surface is by grinding, and also SU hole is for drilling, and the 6 is counterbore, this part, and the tapping will be the threads. All right, next let's look at how to design machine cells. They're actually we're gonna look at it from both the manual and automatic operations, and also sometimes it's in a mix. From the manual operations, it can be one single machine and or multiple machines. For example, the A is one single machine, while the B will be the more a production line, right? Multiple machines with production line, and C will be the mix of both automatic production with the manual operations. Right, you can see this conveyor belt is actually transferring the parts from one station to another, and the workers will work on those parts. When the part goes through, going through on the conveyor. Well, the D will be replacing all the manual operators with automated machines, so that's another setup. The E will be and more like carousel or the setup. So the parts have the parts in from one direction and then parts out from here. So after it goes through all the processes along this production line. Well, the pros and cons about cellular manufacturing. The pros will include the standardizing tools, fixtures, and setups are encouraged in cellular manufacturing. I already explained that. Also, material handling is reduced. You do not have to move here and there to get the parts. And the process planning and scheduling are simplified. It's because if you have to plan out or schedule each of the single step of the composite part, then there's going to be a lot of work. But if you are thinking, hey, that's a work cell that makes that composite part, I just need to schedule that as a whole scheduled part, so whole composite part, then the scheduling work will be a lot simpler than before. And also working process and lead times are reduced. It's because once you put all these processes together, it actually reduces the changeover times and auto setup times. So I also that's why it can reduce the working process and lead times. And the higher work satisfaction in group technology cells. This is because traditionally, if you are the only worker in the work cell, or if you are only worker in one station, a lot of times you feel lonely and you do not have communications, and it's hard to communicate with others. After a while, it's gonna cause some psychological effect on yourself. Well, in a cellular manufacturing, because it involves several machines and several maybe workstations together, then you got a chance to communicate with your coworkers, right? Regardless of what kind of topic you talk about, that's the social communications that is needed as a human being, right? So in this case, actually increases the worker satisfaction in group technology. And also it's higher quality work is because when there's problems, can easy to be found out, and also we know who is responsible for working that. Well, the cons will be it's really hard to code if there are a lot of parts. For example, for a single airplane, right? For Boeing, when you're making airplane, maybe there are tens of thousands of parts in this airplane, but coding those will be a long and a tedious task for them. And also rearranging those kind of production machines will be difficult as well, because it takes time to plan out and how to figure out how to move those machines, and also change the setups in order to make the new uses. All right, last we're going to talk about flexible manufacturing systems. So flexible manufacturing system means that the manufacturing system can actually adapt the environment to make different varieties of products, because the machines are available or have that kind of flexibility to make them. Those kind of machines usually include, CNCs. So CNC means computer numerical control, or some means AGVs, robots, or some other computers. And how do machines work? The machines actually use part programmings. So either it's a cutting process or machining process is actually uses part programs generated by the designers, right? And also, in flexible manufacturing, it's not only just hardware, software, and it also involves the human labor. So the human labor will also be flexible enough in order to conduct different operations. And these are different setups for FMS layouts. So one is the inline layout, and also you can have the ladder layout. So in the ladder layout, it developed different tracks, for around the machines. So the parts will be traveling on the tracks. Well, another one is open field. Open field will be having the parts sitting on the AGV itself. AGV is automated guided vehicles. So automated guided vehicles will be the vehicles that actually travel on the shop floor without anyone driving it. So because they're using some sensors or using certain tapes, tracks on that is taped on the floor, and so it does not need to include in this setup, open field setup. We do not need any hard system of the tracks. Instead, we just only need some of the invisible tracks, so you can travel around those kind of workstations. Also, another setup is robot centered. So you have the centered robot, and then you have different machine tables, work tables, and the parts carousel in order to make the parts. So that's another setup for flexible manufacturing systems. All right, next let's look at how these different production system actually fit in the production environment. Here we have different methods. We have a standalone numerical control machine. So basically we only have one single machine. Also there are manual methods. So manually make some methods, right? We have flexible manufacturing cell, and also flexible manufacturing system, as well as transfer line. So let's look at the transfer line first. So usually for transfer line, it's mostly used for we mainly make one single product, or very limited model of product, because in the transfer line it does not allow that much time for changeovers and setups. It just go one by one and then next, right? So that's why it is very good system for low variety but high volume production, right? Low variety and high volume production. Think of the food processing company, right? Every day you're gonna produce a lot of the food, but it's all the same, right? It's all the same. So that's why the setup will never be changed, or is rarely changed, unless they are making a different food or have another setup, right? So this is a transfer line. Well, the flexible manufacturing system will be on top of the transfer line. The flexible manufacturing system builds certain flexibility of the machine, so they can easily configure it to make another model of the product, and also it can make larger volume compared to standalone machines, and also flexible manufacturing cells. but it won't be, because of the setups and changeovers, it won't be as high volume as the transfer lines. Well, as you can tell, from this line, the standard alone numerical control machine probably it can produce the lowest volume, but it really can have a high variety because it has a lot of flexibility. Think about the 3D printer as an example, right? You can make tens of thousands designs, and then you can always make it from make the part from the 3D printer, right? So it has that kind of flexibility. All right, so that's about the different systems fitting the different production environment. And for this class, we mainly talk about cycle time analysis and also cellular manufacturing. These are the key components in this lecture. All right, that's it.